Now I'm going to talk about uh, the following topics: Slater determinant, excited states of helium, and something called that's sometimes referred to as Hund's-Bessel rule. So those are going to be the main topics for this video. I'll start by talking about the Slater determinant. First of all, a little bit about Slater. John C. Slater, he was mentored by Bohr. He was part of the team that developed this BKS theory that was part of the early quantum theory, one of Bohr's theories related to the hydrogen atom. And it has many of the features of the later Schrodinger theory. So it's kind of a interesting historical development. Slater also was involved in really he was involved in, he wasn't the only person, but involved in really developing the theory for quantum chemistry, and a lot of atomic quantum mechanics as well. He helped to develop the Hartree-Fock theory, sometimes called, or arguably should be called, the Hartree-Fock-Slater theory, because his ideas are certainly central to it. And also was involved in the development of a lot of the key concepts, that led to the band theory of solids in solid-state physics. So Slater's the Slater-Koster tight binding theory is part of that, and so a lot of our understanding of bands and metallic conductors versus semiconductors and insulators, a lot of that can be traced to Slater's work. And Slater was also, somewhat interestingly, he was the mentor of my PhD mentor, Chuck Harris. So I feel some affinity to Slater's work. So let's move on to the Slater determinant. So this is a method or a series of steps that can generate, or kind of like an algorithm almost, that can generate wave functions that have the right exchange symmetry. So far we kind of try to develop them by trial and error and inspection. But if we're going to deal with more and more complex electronic configurations, we need to have something that's a little bit more robust or a little bit more automatic. And Slater's determinant sort of fits that. So we can think of an example that kind of leads us towards the Slater determinant, in that we previously developed an expression for the helium ground state, where you have, it corresponds to sort of like one electron in a spin-up state and one electron in a spin-down state, and they're both electrons are in the 1s orbital. And we ended up with this somewhat long expression, which you can rearrange as a determinant like this, where you have 1 over square root of 2, and then 1s 1, alpha 1, 1s 1, beta 1, 1s2, alpha 2, 1s2, beta 2. So if we multiply out that determinant, we get the expression that we saw in the previous lecture for the helium ground state. And then, looking at this sort of rearranging in this manner can help inspire this Slater type approach to the to generating wave functions with the right symmetry, exchange symmetry. So the method is as follows. And you recall, of course, that a determinant, say of determinant A, B, C, D, that determinant of that matrix is AD minus BC. Okay, and again, so if we multiply out that determinant, we get the wave function that we previously talked about. So let's move on to what the actual method is. The first part is make an energy level diagram. And then from that diagram, list the what we'll call spin orbitals, which are the products of the say 1 electron atomic orbital although this also works for molecular orbitals as well, and the spin wave function. So for example, if we have the helium ground state at the lowest energy state, the energy level diagram looks like this. There's just one energy level that has electrons in it, and it has one spin up, and it's the 1s orbital. It's the energy corresponding to that. And that orbital has 2 electrons in it, one spin up and one spin down. That's the sort of basic energy level diagram, with occupation. Okay, so this is saying we've got, this is giving us a basic picture of the electronic configuration. And then when we want to, we can take this and sort of take it apart and list the corresponding spin orbitals. And that would be 1s alpha. Okay, so this is without the numbers associated, without the parenthetic number, without the labels. So there's a 1s alpha, and then there's a 1s beta. And let's move on. Let's see, and for other systems, well, we can look at other systems later. And well, no, let's look at a couple more. Let's say we had a system where we had a 2px and a 2py orbitals, and we had, say, 1 electron in each of those orbitals. Right, then that would be say, oops. That would be 2px alpha, 2py alpha. Right, that would be a spin-up electron in the 2px orbital and a spin-up electron in the 2py orbital. And so you can, it should hopefully be apparent that what is from whatever electronic configuration given by an energy level diagram showing which electrons are in which orbitals. From that you can then generate this list of spin orbitals. Okay, then the next part is we construct a determinant as follows. Each column has a different spin orbital obtained from the list of step 1. And then we want to leave space for the labels, though. Okay, because we're gonna add those soon. Also, we need to define n, big N equals the number of electrons in the wave function, or we think of it as it's related to the size of our determinant slash matrix. Is it if it's 2 by 2, and there's 2 electrons, then big N, capital N equals 2. And then we add labels increasing with our row number, or be equal to the row number. In other words, and then we need a normalization constant out front, and that's going to be given by, that's going to be related to this number of electrons in our system. So then we construct our wave function as follows. It's going to be 1 over square root of n factorial. And then we have the determinant where we go up with our labels as we move down the matrix or the determinant, and then our spin orbitals are listed as we move across. So, quick example. Let's look at 3 electrons in the 3 different 2p orbitals. And let's make them all spin up. So the spin orbitals then, based on this occupancy diagram, the spin orbitals are 2px alpha, 2py alpha, 2pz alpha. So those are going to be spread out across, there's going to be a column for each of those. And then we add the labels, and then each row has a different label associated with it. So this, so then this is going to give us psi equals 1 over square root of 3 factorial, which would be 3 factorial is 3 times 2, or 6. So it'd be 1 over square root of 6. And we'd have 2px, 1, alpha, 1. So all this whole row is going to, all the labels are going to be 1. Then we go to our next spin orbital, which is 2p y, 1, alpha, 1. And then the next one would be 2pz, 1, alpha, 1. And then we'd have 2px, 2, alpha, 2, 2py, 2, alpha, 2, and then the third one would be 2px, 3, alpha, 3, 2py, 3, alpha, 3, 2pz, 3, alpha, 3. And so this is, looks somewhat complicated, but of course, arguably more compact, or at least somewhat more organized than the full multiplied out version of this Slater determinant. And this is the case. It's easy to see by the time you get to 3 electrons, it gets tricky to try to determine an antisymmetric wave function by hand, but this works. I'm not going to necessarily show that it's antisymmetric with respect to exchange here. We might have a problem, a homework problem where we do that, but I'll leave that up to you to as an exercise. And one thing that's sort of built in to this is that if the determinant is 0, then this is an invalid electronic configuration. In other words, if you try to have a helium where you had 2 spin-up electrons in the 1s, and you try to express the corresponding Slater determinant and then multiply it out, you end up with terms canceling and that the determinant equals 0. And again, I'll leave that as an exercise at this point, or it may be assigned as a homework problem. So this is a handy way of generating various wave functions that are for, the two electron case is fairly straightforward. 3 and so on is going to be more complicated, and this is a fairly robust way of representing these multi-electron wave functions in such a way that they have the proper exchange symmetry, and that, in other words, the fact that we have quantum mechanics, the rules of quantum mechanics state that we have to have to treat identical particles in a certain way. They're either fermions or bosons, and that's going to have certain consequences with respect to how wave functions are. First of all, it puts some restrictions on what kinds of configurations are even allowed. And then it also, as it turns out, as we'll talk about later shortly, it gives us some guidance about the relative stability, or which electronic configurations are lower in energy than others, all else equal. So there's some important consequences that give rise to, first of all, this requirement that you can't have two spin-up electrons in one particular orbital state. The sort of that rule, the 2 electrons per state and 1 spin up and 1 spin down, that is consistent with this anti-symmetry requirement, and of course the anti-symmetry requirement is satisfied by employing the Slater determinant. Okay, so anyways, that's a tool, and we'll go ahead and use it. Now let's move on to the excited states of helium. And I think actually I'll go ahead and do that with the next video.